This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good morning everyone. So today we're just going to continue looking at stability analysis for feedback control systems. So just to remind us of what we're doing, we're looking at a feedback control system. Okay, so there's the feedback path. We've got a nominal transfer function model for the plant. Okay, and I think it's useful to think of the model of the plant as including such things as disturbance signals, and I've absorbed the output disturbance around through to the reference here. It enters the loop in more or less the same way, and similarly for the sensor noise. Okay, so we're interested in understanding when the closed loop will be stable in the sense that bounded signals at the inputs to the closed loop system result in bounded internal signals. Okay, and of course if this is bounded and this is bounded, this must be the bounded because it's just the difference between two bounded signals. Okay, and similarly if this is bounded and this is bounded, this must be bounded. All right, because this is just the sum of this, and so you can think of this as being this minus this. All right, so you can write down the equations by just reading things off the block diagram. Remember, a block diagram is a graphical description of a system of equations. All right, so if we look at this signal y, we can see that it's g times this signal v. That's what I've written in the brackets there. V is equal to d plus this signal here, which is c times this signal here, and this signal here is just r minus y. So if we take this term, which depends on y, onto the other side, okay, we'll end up on the left-hand side with 1 plus gc times y. So if we divide both sides then by 1 plus gc, we get this expression for how y depends on the input d and the input r, and it's via these so-called sensitivity transfer functions. Okay, and similarly we can write down an expression for how v depends on the inputs d and r. So you follow the same procedure, you read off the block diagram what v is. Okay, v is d plus this signal here. This signal here is c times this signal here. So that's c times that signal. That signal there is just r minus y, and y is g times v. So again, taking v on the other side and dividing both sides by 1 plus gc, you end up with this expression here that tells you the relationship between the internal signal v and the input d and r. Okay, so in order for the internal signals to be bounded, when the inputs are bounded, we need all of these transfer functions to be stable transfer functions. In other words, we need them to have all of their poles strictly in the left half part of the complex plane. So if we now say that our plant transfer function is expressed as the ratio of two polynomials, okay, and we'll be dealing with proper transfer functions and controllers, that relates to a physical, the physical notion of causality. Okay, we want the degree of the numerator polynomial to be no greater than the degree of the denominator polynomial, otherwise it'll be like differentiating the input signals, which is not really causal. Okay, so we're going to assume that these polynomials are co-prime in the sense that they have no common factors. All right, so if we've got g expressed as the ratio of two polynomials and c expressed as the ratio of two polynomials p and l, we can substitute those into the expressions for the sensitivity functions. right? So this is one of the sensitivity functions. It's this one here. And just substituting in these expressions for G and C, okay, we can see that you end up with this expression here. Again, this is a ratio of two polynomials. Products of polynomials are just polynomials. Sums of polynomials are just polynomials. So the point of going, substituting these in is so that we can express the sensitivity as a ratio of polynomials as opposed to a ratio of rational functions. Okay, here, these things are themselves ratio of polynomials, as you can see here. All right, so that's where the expression for the so-called output sensitivity function, which also tells you how, you know, this signal relates to this, it tells you how this signal relates to this, and so forth. Okay, so you can see on the denominator here, we have the so-called characteristic polynomial. All right, it can be formed out of the polynomials that are used to define the plant and controller transfer functions, and that polynomial appears on the bottom of the corresponding expressions for the other sensitivity functions as well. Okay, so if we look at this sensitivity function, okay, which is this one here, it's telling you how y depends on r, and go through the same substitution. Okay, this is just reminding you of what lambda is. It's the so-called open loop transfer function. It's just the product of the plant and controller transfer functions. If you like, it's what the transfer function is along here when I've broken the loop. That's why it's called the open loop transfer function. Okay, so if I open that and look at what goes there, it's just the product of these two transfer functions. Okay, so again, just substituting in, it's just all algebra, all right? And you can see all I've done here is say, well, I know what 1 on 1 plus lambda is. It's this guy here, right? And I'm just multiplying by lambda, which is the product of the plant transfer function and the controller transfer function. Okay, of course, this L cancels that L, that A cancels that A, and you're just left with B times P on the top. Okay, this is showing you why this transfer function is algebraically related to this one. I mean, you can see that you know, lambda on 1 plus lambda s is equal to 1 minus 1 on 1 plus lambda, right? Because if we just multiply this term by 1 plus lambda and divide by 1 plus lambda so that it's equal to 1, we get this expression here, and the 1's cancel out, and you're left with this. Okay, and similarly, you can see that the other sensitivity functions can also be expressed in a way that results in the characteristic polynomial being on the denominator. All right, so this guy will cancel this guy. So again, the thing on the denominator is just the characteristic polynomial. This guy cancels this guy, and the thing on the bottom is just the characteristic polynomial. So clearly, if all of the zeros, so all values z that make the characteristic polynomial 0, if all of them lie in the left half plane, then clearly all the poles of these transfer functions, right, including this one here, will lie in the left half plane, because the poles of each of these transfer functions are simply the zeros of the characteristic polynomial. That's what appears on the bottom. Okay, and it turns out to also be a necessary condition, okay, when we take into account that we're assuming that these are coprime polynomials. Right, so in principle, you might think, well, there's always something in the numerator here, all right? So that could end up cancelling out a factor of the characteristic polynomial, right? It's possible, but what's not possible when these are coprime is for an unstable a right half plane 0 of the characteristic polynomial being cancelled out in all of them. Okay, it's just not possible. And there's a little note on LMS that goes through the whole argument to show you why it's not possible. Okay, as soon as the characteristic polynomial has one zero in the right half plane, that will appear in at least one of the closed loop sensitivities. All right, and it's also worth noting that the zeros of the characteristic polynomial coincide with the zeros of 1 plus lambda s. Okay, it is precisely, if you look at 1 plus lambda s, that's this guy here. All right, so if we take these up here and add it to there, we're getting the characteristic polynomial, and clearly the zeros of this will coincide with the zeros of this. All right, so that's why we're interested in studying the zeros of polynomials, which is what we started looking at right at the end of the lecture yesterday. Okay, we noted that in principle you can numerically determine the zeros of a given polynomial numerically. All right, but you need a computer to do that. You could even do some parametric stability analysis by looking at the zeros of a polynomial that's parameterized in terms of something by numerically evaluating the location of the zeros in the complex plane for a grid of that parameter. Okay, but that requires computation, and you don't always want to be doing computation when you're trying to do design. Okay, you want to use some results that don't require computation that inform you about the nature of the zeros of a polynomial. Okay, so clearly when the polynomial is first order, okay, so something that looks like this, we can write down explicitly where the zero is. So analytically we can say where the zero is, and if that's in the left half plane, the coefficient A0 must be positive. All right? And similarly, if you know that the coefficient is positive, then it's telling you the zero is in the left half plane. So the coefficient here being positive is both necessary and sufficient for the zero to be in the left half plane. All right? Analytically, in the case of a quadratic, you can write down where the zeros are analytically. Right? You don't have to compute it numerically, you can write it down. All right? Now, that's something that you've probably seen many times before. So if we apply it to a polynomial where we've normalised the coefficient of the highest power of s, and of course that doesn't change the location of the zeros in any way. Right? If I start with a polynomial that has a coefficient in front of the highest power of s that's not 1, I can factor that out, okay, as long as it's not 0. Okay, but if it was 0, we wouldn't have a polynomial of degree n, we'd have a polynomial of degree n minus 1. Okay, but if it's non-zero, I can always factor it out so that the coefficient of the highest power of s, that's an n by the way, is 1. Okay, so it doesn't, it's without loss of generality that we can, assume that the coefficient of the highest power of s is 1. And if you look at a quadratic with the coefficient of the highest power of s normalised to 1, then the zeros will be located in these two locations. So one at minus a minus the square root of a1 squared minus 4a0 divided by 2, and the other one will be at minus a1 plus the square root of a squared minus 4a0 divided by 2. And so if we know that these are in the left half plane, then it must be the case that A1 is positive and A0 is positive. Okay? If A0 were negative, then it would follow that this number here would be bigger than A1, right? Because we would be adding something to A1 squared, and so when we take the square root of that, we'll get a number that's bigger than A1. All right? And that would mean that there's a right half plane 0, even in the case that A1 is bigger than 0. So A1 bigger than 0 makes sure that that's negative. But in the case that A0 is negative, we would then be adding to that something that's bigger than A1. And so the result would be positive, giving us a 0 in the right half plane. Okay? Clearly, if A1 is negative, then this is positive, and then we're going to add something positive to that, and we'll end up with the right half plane 0. Okay, so this little result here is, this sort of thinking holds in general for a degree n polynomial. Okay, so assuming that we've normalised the coefficient of the highest power of s to be 1, if all the zeros of p have negative real parts, or if all the zeros of the polynomial p are in the left half plane, then it is necessary for all of the other coefficients to be positive. So if you were given a polynomial in this form, okay, really the result's saying that if all the zeros of this are in the left half plane, then all of the coefficients have to have the same sign. Okay? So the implication there is in one direction. It's saying if the zeros are all in the left half plane, then all the coefficients have to have the same sign. Okay? In the case of a first order and second order polynomial, that condition is also sufficient, as we just discussed. But in general, it is not a sufficient condition. Having all of the coefficients of the same sign does not imply necessarily that the zeros are all in the left half plane. And here's a condition, here's an example here. All the coefficients have the same sign, but it has 1 0 in the left half plane and 2 zeros on the imaginary axis. The imaginary axis is not the left half plane. Okay, you've got to be to the left of the imaginary axis. Okay, so this sort of result is used to tell you when the zeros are not all contained in the left half plane. If you have a polynomial and you see that there's coefficients of different sign, right, including a coefficient being 0, when some others are non-zero, then you know that there will be at least 1 0 in the right half plane. Right, so it's almost like a negative result rather than a positive result. Okay, so here's just a little example, right, where we could apply that sort of result to get some conditions on a parameter that must hold in order for it to be possible for the polynomial to have all of its zeros in the left half plane. But because we're going to be dealing with a cubic, it won't be enough. We're just narrowing down the range of parameters for which it is possible on the basis of the necessary condition that we just discussed. So let's consider a system that has this as the plant transfer function. So it has one pole at s equals 0, it has one pole at s equals minus 1.5. Okay, so in open loop it's not really stable because of the pole at s equals 0. Some people would call that marginally stable, but there is a component of the impulse response that does not decay. All right, so I would call that unstable. And let's say our controller looks like this. Right, so don't get confused here that it's written this way. This is really the ratio of two polynomials. On the bottom we've got 0.1s plus 1, and on the top we will have 0.1k plus 1s, okay, plus k. Okay, so the ratio of two polynomials. If in the notation that we've established, that G is B on A, right? That's B, that's A, okay, and we had the notation C was P on L, okay, so that is P and that is L. All right, so the characteristic polynomial phi is AL plus BP, okay, so when you write AL plus BP, this is the polynomial that you get. All right, you can see that the coefficients are parameterized in terms of a controller parameter k. Okay, so where the zeros lie depends on the value of k that you choose. Choose different values of k, the zeros will change location. All right, now, in order for it to be possible for the zeros of this to lie in the left half plane, all of the coefficients have to have the same sign, right? Because if they don't, you know that there's at least 1 0 in the right half plane. So we can use this now to narrow down a range of values for our parameter for which it's possible that this has all of its zeros in the left half plane. In particular, we need this to be positive, right? Because if it were not, it would have different sign to these guys, which would tell us there would be a 0 in the right half plane. And we need this to be positive for the same reason. Okay, so they're the two conditions that must hold in order for it to be possible for this to have all of its zeros in the left half plane. But because it's a degree 3 polynomial, it's not sufficient. So all we've done is narrowed down the range of values for k, right, that might be acceptable from the perspective of the stability of this closed loop. Okay. So what we're going to look at now is something that provides a sufficient condition for all the zeros of a given polynomial to lie in the left half plane, even for polynomials of degree higher than 2. In fact, it works for arbitrary degree polynomials. All right, and it's called the Routh stability criterion. All right, to determine this criterion or to assess a polynomial on the basis of this criterion, you have to build an array of numbers out of the coefficients of the polynomial. Okay, and once you've built the array, the test for when all the zeros lie in the left half plane is that in the first column of this array, all of the numbers have to have the same sign. So again, if we've normalised the highest, the coefficient of the highest power of s to be 1, that'll be a positive number, and we'll need all of the first column of this so-called Routh array to be positive numbers. And if that's the case, then you know that all the zeros will lie in the left half plane. So it's a sufficient condition. It's also necessary, right? So as soon as you get a sign change in this first column, you will know there will be at least one 0 of the polynomial either on the imaginary axis, in which case there will be a pair of them, or in the right half plane. Okay. Now, why this result holds is not easy to see. Okay. The proof is very complicated. If you're interested, there is a proof. You just type it in to Google and it'll take you to a wiki book and it'll show you the proof, but it's complicated, right? Otherwise, there's a proof in the Chu Lee book, but I don't think it goes well beyond the scope of this course to understand how to prove this result. All right. What's more important is to know how to apply it. Okay. So the first step in knowing how to apply it is being able to build this array. Right? And it really is just an array that's built out of the coefficients of the polynomial. Right? So let me just show you how to do it for, where this comes from. Well, not where it comes from, but how to build this array. Okay? So we've got a 4th order polynomial. Let me just give myself a bit more room. We've got A4, S4, A3, S3, A2, S squared, A1, S, A0. Right? This array is just like a matrix, right? And so let's label the rows of the matrix with the powers of S up to the highest power of S. Okay? So we're going to get 5 rows for a degree 4 polynomial. All right? Now, the first row is made out in this way, right? We grab the first coefficient, right? The coefficient of the label of the row, okay? And then we skip one and go to the next one, okay? And then we skip one and we go to, let me just put a little bit more space because I'm going to run out of A2, and then we skip one and we go A0. All right? Now, if you like, this continues down, but there are 0 coefficients, right? So we can just fill in the rest of the row with zeros, okay? Which is necessary to be able to complete some of the subsequent steps. So that's the first row, right? You write down the first row of this array by just reading coefficients from the polynomial, right? The important thing to remember is that you start with the highest degree, the coefficient of the highest power of S, and then you skip one, and each time you skip one as you move along the columns, right? The second row is then made up of the remaining coefficients. So again, you start with the coefficient of the label of the row, right? So we'll get A3, right? Skip 1, A1, right? Skip 1, effectively 0, right? And so on. So the first two rows of the Routh array are very easy to build, right? They just come directly from the polynomial that you're working with. All right? Now we have to construct this row here. And this row is not constructed by just reading things off the polynomial. This row is constructed from the two rows above it. Okay? And it's done this way. You always, in this row, divide by this number, which is called the pivot. Okay? So we're going to divide by A3, and then we're going to take minus the determinant of a 2 by 2 matrix. And that 2 by 2 matrix for this entry is given by these two columns here. All right? So this first term is A4 times A1 minus A2 times A3. All right, so you do the determinant like this, right? And then multiply by minus 1 and divide by the pivot. Okay? So that's the first entry of this row. The second entry of this row is formed in a very similar way. Right? We again divide by the pivot A3. Okay? And on the top we get minus now the determinant of another 2 by 2 matrix. Okay? And the 2 by 2 matrix that we use now has this again as the first column and this as the second column. Right? So the first column of the matrix that you take a determinant of is always the first column of the two rows above the row that you're working on, right? And the second column comes from one position to the right of the column in the row that you're working on, right? Just like for this guy here, we worked with this as the second column. It's one position to the right, right? When we're working on this guy here, the second column of the matrix we have to take a determinant of is one position to the right. So in this case, it'll be A4 times 0, right, minus A0 times A3. Okay? Then we can keep moving along, all right? And, to work out what this guy is, we still need to divide by the pivot, multiply by minus 1 times the determinant of now another 2 by 2 matrix. That 2 by 2 matrix will still have this as the first column, right? And the second column will be one position to the right. Okay? But now, obviously, when we take the determinant, right, we're doing A4 times 0 minus A3 times 0, which is just 0. Okay? So that's that row. Now we have to do the next row, and the next row is built up in exactly the same way from the two rows above. Right, so each row is always built from the two rows above in exactly the way that I showed now. Right? So the pivot changes, okay, because the pivot would now become this guy here. All right, so that's always going to be on the bottom, right, of all things in this row. Okay, let me just give myself a bit more room. Put S0 down here. Whoops. Okay. So we're now working with these two rows in exactly the same as we were working with these two rows before. So you're always working with the 2 rows above the row that you're trying to figure out. Okay, that is always the pivot. That's what goes on the bottom here. And then what goes on the top is again minus the determinant of a 2 by 2 matrix built from the 2 rows above. The first column will always be this. And the second column will come from one position to the right. Right, so to get the number here, the matrix that we're taking the determinant of is this one here. Okay, for this guy here, we'll get minus the determinant of a different matrix, and that different matrix will have this still as the first column and 1 to the right as the second column. Right, so the number that goes in here will be this times this minus this times this. Okay, so it's very algorithmic how you construct this so-called Routh array. All right? So here's what it is in general terms. Okay, that Routh array, of course you've got to keep going, right? You've got to keep going. Don't try to, this is just to show you what's going on. The algorithm will come in a second, right? So you keep on going until you get to the last row, right? So that's really given a degree n minus 1 polynomial. The array that we're constructing is an n by n matrix. Okay? And as we saw, the first 2 rows just come from the coefficients, right? So the first row will start with the coefficient of the highest power of s, all right? That's what this guy is. Then we skip one. That's what this guy is. Then we skip one and then build all these up. Okay? Now to get n things here, right, you might be putting a lot of zeros in here, right? So you will put a 0 in here for the last one that you might have to end up looking at in the same way as shown in the example. The second row, again, just comes from the coefficients of the polynomial, right? So it starts off with this one, then you skip one, that's what that is, then you skip one, and so on. All right? The subsequent rows are then built in the way that we showed. Each row here is built from the 2 above, no matter where you are, right? So each row is built from the 2 above it, right? And it's built from the 2 above it in this way here, right? So you've got minus 1 divided by the pivot, okay? So the pivot is always the entry in the row immediately above and most to the left. Okay, so for the third row, that's the pivot. For the fourth row, it'll be the 3-1 entry that's the pivot. For the fifth row, it'll be the 4-1 entry that's the pivot. Okay? So that's the same no matter which position you're looking at along the row. What changes is the matrix that you take the determinant of, right? The first column of that matrix is always the first column of the 2 rows above. The second column of that matrix is always the column 1 position to the right, right? That's why it's k plus 1 from the 2 rows above, right? So we're looking at LK, right? So we're looking at the lth row, kth column, all right? We're looking at the 2 rows above, right? The first column here is from the first column of the 2 rows above. The second column here is from the column 1 position to the right in the 2 rows above. You take the determinant is this times this minus this times this. Okay, multiplied by minus 1 divided by the pivot. So that's the general algorithm, okay, for how to construct the Routh array. Okay, it's doing, it's just formalising what I was trying to show you here. Okay, now, let's now apply that to this example. Right, so this is just writing down all of the numbers that I didn't bother writing down here when I'm just trying to show you how it works. All right, so you can see that I've got in the first row, starts with the coefficient of the highest power of s. We've got a degree 4 polynomial here. Then we skip one, and then we skip one. Second row just starts from the remaining, is built from the remaining coefficients, right? A3, skip one, A1, and if you run out of coefficients, you put a 0 in. All right? This is the pivot. We've got 1 minus 1 divided by the pivot here, minus 1 divided by the pivot here. All right? What's on top here is this times this minus this times this. All right? It's the determinant of a matrix where the first column is the first column of the 2 rows above, and the second column is the column 1 position to the right of where you're working from the 2 rows above. Right, so it's that times that minus that times that. This guy here, again, it's got 1 minus 1 divided by the pivot. That's the pivot. Okay. And on the top, we've got the determinant of a matrix that has first column, that is the first column of the 2 rows above, and the second column is the column 1 position to the right from the 2 rows above. Right, so it's A4 times 0 minus A0 times A3. That's what that is. Okay, which turns out to be equal to A0. Now we do this row here. Okay, this is built from the 2 rows above in exactly the same way. This becomes the pivot, right? So we've got minus 1 divided by the pivot. Okay, and the number on the top here is that times this number minus that times this number. Okay, this guy here will still be minus 1 divided by the pivot. Okay, but we end up with 0 here because you can see that the matrix we have to take a determinant of has this as the first column and this as the second column. And of course, if you've got a column of zeros, the determinant is 0. And you keep going. Right, this guy here is minus 1 divided by the pivot. Right, and on the top we have this times this minus this times this. Right, so that's just an algorithm for constructing this array. If all of these have the same sign, then the polynomial has all of its zeros in the left half plane. Now you might end up, having a 0 somewhere in the first column at some point. So let's say coefficient A3 was 0. That would stop you from dividing here. But that shouldn't stop you from building the array. What you do is you replace 0 by a symbol, call it epsilon, right? And keep working with the symbol, right? The epsilons will appear in all of the subsequent calculations. And then you look at what happens when that variable goes to 0. You take the limit as it goes to 0 in the end, right? And if you take the limit as that thing goes to 0, when you work out all these numbers, and you get no sign change in the first column of the Routh array, then you know the polynomial has all its zeros in the left half plane. Okay? So it's just very algorithmic. So let's apply it to this polynomial. Okay? The first row, right, consists of this coefficient and this coefficient. All right? The second row consists of this coefficient and this coefficient. This guy here is minus 1 divided by this, times this, minus this, times this, which gives you that. Of course, it depends on k because these coefficients depend on k. Right? This will be 0, right, because this term here will be minus 1 divided by this, times the determinant of a matrix that has this as the first row and 2 zeros as the... Sorry, this is the first column and a pair of zeros as the second column, which means the determinant is 0. Then this guy is minus 1 divided by this as the pivot, times the determinant of this times this minus this times this, which of course gives you k back again, right? Because this times this divided by, this is just k. All right? So we want no sign change in the first column. All right. In other words, we need this to be positive and we need this to be positive. Okay, so they're the two conditions that are written down here. Of course, this being positive implies this, right? Because this just requires 3k on 230 to be greater than minus 2.5. In other words, it requires k to be larger than some negative number. So this condition trumps, okay? And it turns out that in this particular case, the necessary condition that we found up here is also sufficient, right? But these conditions are just coming from saying, well, this is a positive number, this is a positive number, I don't want any sign changes, so this must be a positive number, and this must be a positive number. All right? So the necessary and sufficient requirements on k for this polynomial to have all of its zeros in the left half plane is that k needs to be a positive number. Right? So for any positive value of k, this closed loop system will be stable. All right. This is now applying the result in a slightly different way to determine when the zeros of a given polynomial lie to the left of a line that's parallel to the imaginary axis. So this is being used to tell us when the zeros, let me change the pen, when the zeros lie to the left of the imaginary axis, right? It's telling us when it lies to the left of here, right? We might be interested, for example, when do the zeros lie to the left of a line parallel to the imaginary axis that intersects the real axis at -1, right? Why? Well, remember that the zeros of this correspond to the closed loop poles, right? So if we can find out for what values of k the closed loop poles lie to the left of -1, then we know that the impulse response of the closed loop system will have things that decay faster than e to the minus t, right? Because the real part will always be less than -1, right? Whereas if we're just testing when it's to the left of the imaginary axis, then we just know that the impulse response of the closed loop system will decay, right? But if we end up with a pole that's very close to the origin here, or have real part that's very close to the imaginary axis, it could take a long time to decay, right? Whereas if we know they're to the left of -1, then all components of the impulse response of the closed loop transfer functions will decay faster than e to the minus t. Right? So we can still apply the Routh criterion, but we have to apply it to a transform version of the polynomial. And the transformation simply corresponds to moving the origin to here, so that this now looks like the imaginary axis. Right? Because the Routh criterion is tailored to things being left of the imaginary axis. All right? So if we want to know when are the zeros of a polynomial going to be left of a line that's parallel to the imaginary axis, we just have to move the imaginary axis to that line. Right? And the transformation that moves the imaginary axis to the -1 line is as shown here. Right? So when S is equal to -1, W is 0. So if you like, this is the S-plane, right? And the origin of the S-plane is here, right? This is the W-plane, and the origin of the W-plane sits on S equals -1, right? Because S equals -1 makes W equal to 0. Okay? So the real part of W will be less than 0 if and only if the real part of S is less than -1. Okay, so if we define a new polynomial now as a function of W in the way shown here. Okay, so we evaluate the original polynomial at S equals W minus 1. So this is just rewriting this. Okay, so now when I evaluate this polynomial at S equals W1, I get a new polynomial in W. All right? So you can apply the Routh stability criterion to this new polynomial, right? Remember, the W plane has its origin here. So when we apply the Routh criterion to this polynomial in W now, it's going to tell us when the zeros of this polynomial lie to the left of the W plane's imaginary axis. All right? So if that's the case, then the zeros of the original polynomial must be lying to the left of -1. Right? Because all we've done here is a transformation of variables to move the origin to a new spot. Okay? So the new polynomial, this is the same polynomial as we had before. The new polynomial is defined from that, okay, through this change of variables, if you like. So we now get a new polynomial in W. Okay, you can see that it's got different coefficients to the original one. All right, we can build the Routh array for this polynomial. The Routh stability criterion says, well, if all of these have the same sign, okay, then the zeros of this polynomial in the W plane will all have negative real part. There's the W plane. So if all of these have the same sign, the zeros of this polynomial all lie to here, right? But the values of W that make this 0 are related to the values of S that makes this 0 via this transformation, okay, in the obvious way. So if we satisfy the stability criterion here, it tells us that all the zeros of this lie to the left of the W plane's imaginary axis, which is this guy here, which is the same as saying all the zeros of this lie to the left of -1 in the S plane. All right? So, this is just constructing the Routh array in the same way as before. The first row here is built from this coefficient and this coefficient. The second row from this coefficient and this coefficient. For this row, this is the pivot, right? So this number here is -1 divided by 0.85 times this, minus this times this, and that'll give you this. It depends on K because these two things depend on K, right? This guy here is -1 divided by this pivot times the determinant of the matrix with this as the first column and this as the second column, right? So we at 0.85 times 0, right, minus this times this, which gives you this. And so the requirement is that there are no sign changes in the first column. All right, so we need this to be positive because these guys are positive, and we need this to be positive. So that gives you the two conditions. All right, and these two conditions correspond to this bound on K. So we saw before, in order for this to have all of its zeros in the left half plane, we just needed K to be positive, right? But if we want the poles, the zeros of this, which are the poles of the closed loop with this as the plant and controller transfer function, to all lie to the left of this line that intersects the real axis at -1, so that all closed loop transients decay faster than e to the -t, I need more than K just being positive, right? I need K to be bigger than some number, but I also need K to be less than some other number. Okay, and that's just coming from these two conditions here. All right? So this is a useful little result, okay, for testing stability, right? But all it's doing is telling you whether or not the zeros of a polynomial lie to the left of a line that sits parallel to the imaginary axis. It doesn't tell you where they are for different values of K. All right? So it's just a stability test, right? We can play tricks like this to, change which left half plane we're talking about, but it's still just a stability test. This doesn't tell us where they are, where the zeros of this polynomial are for values of K in this range. It just tells us that they're somewhere to the left of this line. All right? And what we'll look at on Tuesday next week is another way of assessing the stability of a closed loop by looking at the characteristic polynomial, okay, but by making it look like this, all right? And this is the root locus stuff, right, that's mentioned on the first slide. So we'll look at that on Tuesday, and then on Thursday we'll look at the first part of problem set 3. Okay.
When you're trying to get all the coefficients as the same sign, zero count as a positive or negative or neither?
Yeah, so 0 is a, so if you end up with a 0 in this column,
Yeah.
then when there's other coefficients that are positive, then you're failing the test.
Okay.
So they all have to be positive.
Okay, cool. Okay, so zero sort of counts as something, but just not
Well,
positive.
0 is not positive,
Yeah, it
right?
counts
It's
as okay.
0 is non-negative, but it's not positive.
Cool.
Yeah.
Thank you. That makes sense.
This is a question from a while back. So here you says that so the steady state output has no offset to the reference.
Yep.
So for this statement, which sensitivity function does that correspond to? That's
This one. Yep. Because that's the transfer function from R to Y.
Yeah, and
Okay.
then so
So
if we apply the final value theorem to it, we get that
yep.
this transfer function times s, and take the limit of s to 0, we get 1. Is that what we should expect?
Well, you're probably better off looking at the error signal, right? So the error signal will be 1 on 1 plus GSCS times RS, right?
Yeah.
And so if you look at this, right,
But that will go to 0.
it's 1 on 1 plus lambda S, RS, right?
Yep.
And so now you're saying, well, RS is equal to 1 on S. That's a step,
Yep.
okay? And so that gives me ES will be 1 on 1 plus lambda S times 1 on S, right?
Yep.
And so if this is stable, we know that the step response will go to a constant value. So the final value theorem applies. So we get the limit as S goes to 0 of S times ES will be S, right? Times 1 on 1 plus lambda S times 1 on S. That'll go,
Yep.
right? And so we'll just be left with 1 on 1 plus lambda 0,
Yep.
right? But lambda S is equal to, in this
Yes,
case,
times CS.
it's K times 100 on S 0.01 S plus 1,
That goes to
Right.
infinity.
and in the limit as S goes to 0, that goes to infinity, and then you get 1 plus 1 divided by 1 plus infinity, which is 0.
Right. Okay.
Make sense?
Yep. I just
So that
Oh,
point
yeah,
is
sorry,
there
go ahead.
because if we look at this example,
the
so the steady state value, there's always some offset,
yep.
right? Because if you do this, then lambda S, sorry, am I allowed to, is it okay for me to write on this?
Yeah, sure.
Yeah.
Go ahead.
G of S, C of S, in this case, it will be K times 100 on 0.01 S plus 1, right? So in the limit as S goes to 0, this goes
It's
to
some constant.
K
Okay.
times 100 on 1,
Yeah.
right?
Yeah.
So 1 on 1 plus lambda 0 will be 1 on 1
So
plus
the-
K
the
times
arrow
100.
function doesn't go to
So it doesn't go to 0,
Right. Yep.
but as you increase K, the error goes down.
Okay.
Does that make sense?
Yeah.
Right, whereas here, didn't matter what value K was,
That,
doesn't matter what K is, goes to infinity,
yep.
no matter what K is.
Yep. Yep.
So even when K was small, we've got 0 error,
Yep.
right? And the reason is because this here is giving you infinite gain at DC,
Yep.
right? Whereas here, increasing K pushes this line up. So it increases the gain at DC, but it's never infinite,
Right.
right? Whereas having the S will make it